Good morning. It's my pleasure to start the course, especially in the area which has made major input in the development of mathematics. The subject of this course, geometric modeling, is becoming increasingly popular in the computer science. I will also use the term shape modeling, which means a broader class of models and modeling techniques. We will clarify the difference later. So, just for a reminder, all course materials are available via the link mentioned in this slide. The subject of this lecture is Introduction to Shape Modeling. So here we are going to discuss some familiar concepts from linear algebra, analytical geometry, and set theory. Probably you already know all these things and you will just refresh your memory. So let's start. We will try to cover the following topics. At first, it's quite useful to know different points of view at the shape term definitions. Then we'll introduce notion of point, shape and shape dimension, metrics and coordinates used in this course. We'll also discuss different ways of defining point sets. During the lecture and at the end of every lecture, I will give you the list of reference materials. This is a detailed list of notions we need to recall from linear algebra and analytical geometry. There are affine and Cartesian coordinates, Descartes' conception of geometry, point sets, shape and point notions, spaces, linear space, affine space, metric space, Euclidean space, space dimensions, vector space, dot product and cross product. So, one can start remembering some boring lectures from his first courses of high school. And yes, geometric modeling is the place where all these concepts can be useful. But at the beginning, let us discuss different points of view at the very notion of shape. The Longman Dictionary of Contemporary English defines shape as the outer form of something that you see or feel. This definition stresses that shape is given to us through certain human senses such as vision and feel of touch, tactile feelings. German mathematician David Hilbert mentioned summing up his abstract approach to both geometry and mathematics as a whole that one must be able to say at all times, instead of points, straight lines and planes, tables, chairs and beer mugs. He turns us back to original understanding of geometry as a science of measuring land. More abstract definition, which can be found at the Princeton WorldNet Online Dictionary, says that shape is the spatial arrangement of something as distinct from its substance. For example, we are talking about a wooden table. The word wooden refers to substance and the word table refers to both shape and object function. German mathematician Felix Klein first of all wanted to answer the question, what is the problem of geometry trying to solve? In his well-known Erlangen program in 1872, Klein proposed a new unified approach to geometry by starting with a set and a group of transformations of the set. He specified the properties of the geometry as those properties which are invariant under a group of transformations. Thus, he gave two important for us definitions. A geometrical figure, shape, is a set of points. Shape is the geometric information invariant to a particular class of transformations. For example, for Euclidean motions, it's translation and rotation. The distance between points is invariant. One of the modern theories of shape opposing Klein's approach is given by Michael Layton in his book A Generative Theory of Shape, Lecture Notes in Computer Science. The generative theory of shape represents a given shape by a program, procedure that generates a point set. The program must be inferable or recoverable from the point set. This means that the shape acts as a memory store for the generative operations of the program. This idea gives the author the ground to propose his controversial definition that geometry is equivalent memory storage or generative operations. So, you probably know about Grasshopper 3D application that allows us to construct such geometric objects via this generative approach. So you can describe a procedure how to construct difficult geometry, and later you can use it in your applications. So it's quite interesting and straightforward approach where all this notion from this course, linear algebra concepts, ideas, some understanding of nature and dimensional spaces can be useful if you're interested in generative approach for geometric modeling. In the modern century, several European institutions started a joint project called AIM at Shape. AIM at Shape is aimed at coordinating research on representing, modeling and processing knowledge related to digital shapes. In this project, the following definition of shape was given. Shape means any individual object having a visual appearance which exists in some 2-3 high dimensional space. Pictures, sketches, images, 3D objects, videos, 4D animations, and others. They also gave a list of main shape characteristics, such as shapes have a geometry, the spatial extent of the object. They can be described by structures, object features, and part-whole decomposition. They have attributes, colors, textures, names attached to an object, its parts and/or its features. They have semantics, meaning or purpose. They may also have interaction with time, history, shape morphing, animation, video. As we can see, these are application characteristics rather than mathematical properties of shape. Such approach stems from the application character of the project itself. We will consider a shape as a point set in n-dimensional geometric space, for example, in Euclidean space. Usually n will be equals 2 of 3. This definition contains several basic geometric notions, which will be useful in our course: point, dimension, Euclidean space, affine space, linear space, and so on and so on. We will recall these notions in a step-by-step logical manner, as it is done in linear algebra and analytical geometry. The key element of the given definition of shape is a point. Everyone has intuitive understanding of a point as a small ball of infinitely small radius sitting on a line, as it marked in this slide in the right top area. Point here is marked by a dot, and its name is P here. Also, this point can sit on a plane or in a three-dimensional space. However, this notion can be introduced a bit more formally. There are two approaches to defining a point: geometric, originated by Euclid, and algebraic, from linear algebra and analytical geometry. You can see the definition of point provided by Euclid in this slide. The description: a point is that which has no path, indicates that Euclid treats a point as having no width, length, or breadth, but as an invisible location. Usually, axiomatic theory is built on some undefined notions given by common sense. A point, practically, is an undefined fundamental term of geometry. The logic of the point introduction in linear algebra and analytical geometry is as follows. A point is considered as an element of an affine space. An affine space is a set with every ordered pair of points associated with an element of some linear space, vector space. A linear space is a set closed under operations of element addition and scalar multiplication, satisfying certain conditions. If you don't scared by these formal terms, in the previous slide we can define in more detail how vectors and points are introduced in linear algebra and analytical geometry. We need the notions of vectors and affine spaces for this. A linear or vector space definition is based on the following terms. Two types of elements of vector space are: the first one is scalars or real number, just like, I don't know, 1/2, 1, 2, 3, 4, 5, 3/3 or something like that, which will be denoted like alpha, beta, and other Greek letters. So the second element is vectors or n tuples of real numbers. They are denoted like u, v, w, and so on. Also, such operations are specified: addition, multiplication by scalar, and subtraction. From the arithmetics, we know the following properties of scalars. Operations of addition and multiplication are defined for scalars and satisfy such properties shown. Scalar operations are associative, commutative, and distributive. Special scalars such as 0 and 1 exist with the following properties. So, I'm not sure that these scalars and these properties can be quite useful in practical tasks and real geometric modeling, but for general it's quite useful to know about their existence in vector spaces. For vectors, operations of addition and multiplication by scalars are also defined with mentioned properties. In order for a set V to be a vector space, the following conditions must be held for all its elements: u, v, w, and any scalars are as shown. So, also, some of these properties of vector space will be useful for you when you start doing your practical assignments, and it's better to recall it now. Now let us define coordinates of vector. Two vectors are linearly independent when one is a multiple of the other. A basis of n-dimensional vector space is defined as a set of n vectors v sub 1, v sub 2, etc. v sub n that are linearly independent. Each vector v in space can be written as a linear combination of the basis vectors with coefficients from a sub 1 to a sub n. So, you can see all these things stated in this slide, and this property of vector space is basis for constructing so-called Cartesian coordinate, which we are familiar with. So it is a theoretical basis for us to describe all points by just number of real numbers and describe geometric models as a set of points. Dimension of affine space is equal to dimension of associated linear space. Dimension of linear space is equal to maximal number of linearly independent vectors. So you can remind that in 2D we can find only two independent vectors, and all three vectors will be obviously dependent, and in 3D the maximum number of independent vectors will be what? Yes, it will be 3. Now we can define coordinates of the point using coordinates of the vector. So we have two spaces, affine and linear one. We can select the point O in the affine space as the region. Then, for any points P from the affine space, we associate the pair OP with the vector V of the linear space. Coordinates of the vector V are called affine coordinates of the point P. As we could see, a vector is an element of a vector or linear space. It is a quantity in which both the magnitude and the direction must be stated. It can be represented as a directed straight line segment, as we can see in this slide. Consider all locations in relationship to one central reference point called origin. Vector has direction according to origin and length in n-dimensional space. Vector can be defined by two linear scalar arrays as start and end points, or by one linear scalar array for the endpoint with 0 coordinates as start point by default. Now let us finally discuss how we can use vectors in computer graphics. First of all, we use them to represent positions of vertices of objects, to determine orientation of a surface in space. Also it calls surface normal. To represent relative distances and orientations of lights, objects, and viewers in 3D scene. Vectors from light source to surface. So the rendering algorithms can create the impression of light interacting with solid and transparent objects. So you can mention that in modern cartoons, for example, all objects have shadows. So how it can be done? Of course, some multiplicators have to introduce to the scene light source and define how it actually bright, yes? And we also use vectors to define this thing. And the last one is using vectors for representing of force, velocity, throw, etc. So to make our scene, let's call it live, and to create animation or some object with history, some time dependency, to introduce time dependency into modeling. This slide illustrates the operation of addition in 1D space. So this operation for vectors is quite equivalent for just adding two real numbers. And here you can see how we can illustrate it. And we're introducing a 0 point and introducing directions. Of course, in 1D there is no too many directions that we can consider, and I think that this picture is quite obvious for everyone in the class. In two-dimensional space, vector W is added or subtracted to vector U using the parallelogram rule. Drawing the vector V, then drawing the vector W, taking care to place the tail of the vector W at the head of vector V, and finally drawing a vector W plus V from the free tail of vector V to the free head of vector W. So, of course, you can recall that there is an associative rule that says that V plus W equals W plus V, and we could get it from this illustration. And Here the upper picture illustrates addition operation and the lower one subtraction. This slide illustrates the following. The rules for operations in 3D are the same as for 2D. If we represent each vector as linear combination of basis vectors I, j, k, the operations are formally defined as shown. Practically, we have to apply scalar operations of the same type to vector coordinates. The addition may be represented graphically by placing the start of the arrow B at the top of the arrow A, and then drawing an arrow from the start of A to the top of B. The new arrow drawn represents the vector A plus B, as illustrated below. This addition method is sometimes called the parallelogram rule, because A and B from the sides of a parallelogram and A plus B is one of the diagonals. If A and B are bound vectors, then the addition is only defined if A and B have the same base point, which will taken also be the base point of A plus B. One can check geometrically that A plus B equals B plus A, and also one can check the commutative rule. Subtraction of two vectors can be geometrically defined as follows. To subtract B from A, place the end of A and B at the same point, and then draw an arrow from the top of B to the top of A. That arrow represents the vector A minus B, as illustrated below. If A and B are bound vectors, then the subtraction is only defined if they share the same base point, which will then also become the base point of their difference. This operation deserves the name subtraction because A minus B plus B equals A. Vector may also be multiplied by a real number r. In mathematics, numbers are often called scalars to distinguish them from vectors, and this operation is therefore called scalar multiplication. By this moment, we discussed affine geometry, which includes scalars, points, vectors, and their operations. A typical modeling computer graphics system deals with Euclidean geometry, because affine geometry lacks angles and distances. To extend the affine geometry, we need a new operation, inner or dot product, which gives length, distance, normalization, angles, and orthogonality. So, I think you remember what dot product is, but I'll recall. Dot product of two vectors is a real value, not a vector, yeah? It can be calculated by the following expression. U dot v equals u sub 1 multiplied by v sub 1 plus etc. plus u sub n multiplied by v sub n. In the slide, you can see also matrix form of the definition of the dot product. The dot product of two vectors, u and v, is also defined by the following expression. You can see it in the slide, and here you can see the lengths of vectors and also the angle between these two vectors involved in the calculation of dot product. Geometrically, this means that u and v are drawn with a common start point, and then the length of u is multiplied with the length of that component of v that points in the same direction as u. So, or we can say that we need to project one vector to the other and then multiply their lengths. The dot product is intensively used in geometry and its applications for first, defining length or magnitude of a vector, normalizing vectors, measuring angles between vectors, determining if two vectors are perpendicular, finding the length of a vector projected onto a coordinate axis. The dot product of a vector with itself is the square of the length of a vector. The length, or the norm, of the vector is the square root of the dot product. If the norm of the vector is equal 1, the vector is called a unit vector. To make a vector into a unit vector, we need to normalize it as shown by the formula below. The unit basis vectors are called the standard basis vectors. Any vector can be expressed as the sum of scalar multiplies of the standard basis vectors. An angle between vectors can be calculated using two independent definitions of a dot product given above. It is equal to the inverse of cosine of dot product between normalized vectors. Projections of the vector u on vector v can be calculated without angle values as shown in the slide. Dot product of two vectors x and y is defined as follows. X dot y is equal to sum of corresponding coordinates multiplied with each other. Note that this operation takes two vectors and returns a scalar quantity, not a vector. Two vectors are orthogonal if their dot product is equal to 0. In 3D space, three vectors can be mutually orthogonal and linearly independent. Two subspaces A and B of vector space are called orthogonal subspaces if each vector in A is orthogonal to each vector in B. The cross product, also called as vector product or outer product, differs from the dot product primarily in that the result of a cross product of two vectors is a vector. The cross product u and v is a vector perpendicular to both vectors u and v and is defined by the shown expression. In the matrix form, cross product is defined by the following way. This matrix expression defines the norm and the direction of the vector. The problem is that there are two unit vectors perpendicular to both b and a. Which vector is the correct one depends upon the orientation of the vector space. The vector triple ijk is called right-handed if the three vectors are situated like the thumb, index finger and middle finger pointing straight up from your palm of your right hand. The next step is to introduce a metric in a affine space. A metric is a non-negative function g of two variables u and v describing the distance between 2 points for a given set. It satisfies the triangle inequality. Sum of the metrics for two sides of a triangle is greater than the metric for the third side. It is symmetric. The metric does not depend on the order of points in a pair. It also satisfies the condition that the distance of a point to itself is equal to 0. Then they define some metric for the affine space. It becomes a metric space. Thus, an affine space with a metric is called a metric space. So now we come to the Euclidean space. Actually, it is the just particular example of metric affine space, where the metric defined as the function d, you already know it from the school and university, and it's presented in this slide. So, for example, the space of all n tuples of real numbers with the Euclidean metric is an Euclidean space En. In this slide, you can see the Euclidean distance from a point with coordinates x, y to 0 in two-dimensional space and in multidimensional space, which is just a square root of a dot product. The term Cartesian is used to refer to René Descartes' conception of geometry. French philosopher introduced in 1637 in his works. which is based on the representation of points in the plane by ordered pairs of real numbers, so-called Cartesian coordinates. This idea allows geometric relations to be expressed by means of algebraic equalities in analytical geometry. The Cartesian coordinates in two-dimensional or three-dimensional spaces are defined by two or three mutually orthogonal lines intersecting in the region. They are called axes. Point coordinates are taken as distances from the region along each axis. One, two, and three-dimensional real coordinate systems are shown in this slide.